Hello everyone, welcome back to SHR Trinity. In today's video, we are continuing our machine learning interview question series. This is part 2, where we will dive deep into core machine learning algorithms, covering questions 11 to 20. Whether you are a fresher or preparing for an AI engineer or data scientist role, these detailed explanations and comparisons will strengthen your foundational and practical knowledge. Let's begin. Before we dive into the questions, let's look at what we'll be covering in this video. We will cover the core machine learning algorithms. We will explain linear and logistic regression, decision trees, random forests, k-nearest neighbors, support vector machines, naive Bayes, and then dive into ensemble methods, comparing bagging and boosting, and wrapping up with XGBoost. Question 11. Explain linear regression. Linear regression is the simplest and most foundational supervised learning algorithm used for predicting continuous values. It assumes that there is a linear relationship between the input feature, x, and the continuous output variable, y. Mathematically, it expresses this as y equals beta 0, which is the y-intercept, plus beta 1 times x, which is the slope, plus an error term epsilon. The algorithm finds the best fit line using ordinary least squares, or OLS. OLS minimizes the sum of squared differences, called residuals, between the actual target points and the predicted points on the line. For linear regression to perform optimally, the data must satisfy key statistical assumptions. These include linearity, meaning the relationship is indeed linear, homoscedasticity, which means the variance of residual errors is constant across all predictor levels, independence of errors, meaning data points are not correlated, and normality, stating that the residuals should follow a normal distribution. Look at the code on screen. We import linear regression from scikit-learn, fit it on our training features and targets using model.fit, and generate predictions using model.predict. Question 12. Explain logistic regression. Despite having the word regression in its name, logistic regression is a supervised classification algorithm used to predict binary outcomes, such as spam or not spam, or fraud or not fraud. Instead of fitting a straight line, it models the probability that a given input instance belongs to a specific class. It does this by feeding a linear combination of inputs, represented as z equals weights transpose x plus bias, into the sigmoid activation function. The sigmoid function, which is p equals 1 divided by 1 plus e to the negative z, maps any real-valued number into a strict probability range between 0 and 1. To make a final class decision, we apply a threshold, commonly 0.5. If the probability is 0.5 or higher, we classify it as class 1, otherwise class 0. To optimize the weights, the model does not use ordinary least squares. Instead, it minimizes the binary cross-entropy loss, also known as log loss, using gradient descent. Question 13. What is a decision tree? A decision tree is a flowchart-like structure used for both classification and regression. The tree starts at a single root node and splits the dataset recursively into smaller subsets based on feature values. Internal nodes represent a decision rule or test on a feature, branches represent the outcome of that test, and leaf nodes represent the final class label or regression value. To determine the best feature to split on at each step, the algorithm uses mathematical criteria. For classification, it measures the reduction in impurity, using Gini impurity or information gain, which is based on entropy. For regression, it minimizes the mean squared error. The main advantage of decision trees is their high interpretability, as the rules can be easily visualized. However, their primary drawback is a high tendency to overfit the training data by growing extremely deep, complex trees that memorize noise. To prevent this, we must restrict growth using hyperparameters like max depth or apply pruning techniques. Question 14. What is random forest? Random forest is a robust, meta-estimator ensemble learning algorithm that constructs a multitude of decision trees during training. It is built on the principle of bootstrap aggregating, or bagging. It trains each individual decision tree independently in parallel on a random sample of the training data chosen with replacement, which is bootstrapping. Furthermore, it introduces feature randomization. When splitting a node, it only considers a random subset of the total features. This random selection decorrelates the trees, ensuring they do not all make the same errors. To make a final prediction, random forest aggregates the predictions of all the individual trees. For classification, it takes a majority vote. For regression, it averages the predictions. This averaging process dramatically reduces model variance and prevents overfitting, making random forest one of the most reliable and highly accurate algorithms out of the box. Question 15. What is k-nearest neighbors? K-nearest neighbors, or KNN, is a simple, non-parametric, and instance-based supervised learning algorithm. It is referred to as a lazy learner because it performs virtually zero computations during the training phase. Instead, it simply stores the training dataset in memory. When a new query point needs a prediction, the algorithm searches the entire training dataset to calculate the distance to all points. It typically uses distance metrics like Euclidean distance, Manhattan distance, or Minkowski distance. It then identifies the k closest training instances. For classification, the final prediction is the majority class label among these k neighbors. For regression, it is the mathematical average of their target values. The parameter k is crucial. A small k, like k equals 1, is highly sensitive to noise and can overfit. A large k smooths out the decision boundary but might include points from other classes. The major disadvantage of KNN is its computational cost during test time, as calculating distances to millions of rows is slow and memory-intensive. Question 16. What is support vector machine? Support vector machine, or SVM, is a powerful supervised algorithm primarily used for binary classification. The objective of SVM is to find an optimal decision boundary, called a hyperplane, in an n-dimensional space that splits data points of different classes. SVM does not just find any boundary, it specifically searches for the hyperplane that maximizes the margin. The margin is the distance between the hyperplane and the closest data points of any class, which are called support vectors. These support vectors are critical because they determine the position and orientation of the boundary. If the data is not linearly separable in its original space, SVM employs the kernel trick. The kernel trick mathematically projects the input features into a higher dimensional space where they become linearly separable, allowing SVM to draw complex, nonlinear boundaries using linear operations in that new dimension. Question 17. What is naive Bayes? Naive Bayes is a collection of classification algorithms based on Bayes' theorem, which calculates the conditional probability of a class given the input features. The algorithm is called naive because it makes a strong, often unrealistic assumption. It assumes that all input features are completely independent of one another given the class label. For example, in a text classifier, it assumes that the presence of one word in an email does not affect the probability of another word appearing. Despite this oversimplification, naive Bayes is highly efficient. It requires very little training data to estimate parameters, computes predictions extremely quickly, and performs exceptionally well on high-dimensional text-related tasks. This makes it a standard baseline for spam filtering, document categorization, and sentiment analysis. Question 18. What is Ensemble Learning? Ensemble Learning is a machine learning strategy that combines the decisions of multiple individual models, referred to as base learners, to produce a single, superior prediction. The main idea is that a group of diverse, weaker models will collectively make fewer errors than any single model alone. There are three primary ensemble strategies. First, bagging, which trains multiple identical models in parallel on different bootstrapped samples of the data and aggregates their outputs. This is best for reducing variance. Second, boosting, which trains models sequentially, where each subsequent model focuses on correcting the errors made by its predecessor. This is best for reducing bias. Third, stacking, which trains completely different base models, like an SVM and a decision tree, and feeds their predictions into a final metaclassifier that learns how to best combine them. Question 19. Bagging versus boosting. Look at the comparison table on screen. In bagging, such as in a random forest, models are built in parallel, completely independent of each other. Each model is trained on a bootstrapped subset of the data, and their outputs are aggregated through simple voting or averaging. This reduces variance and prevents overfitting. In boosting, such as in XGBoost or gradient boosting, models are trained sequentially, meaning each model depends on the previous ones. The training data points are adaptively weighted so that instances misclassified by earlier models receive higher weight in the next round. The final prediction is a weighted sum of all models based on their individual accuracy. Boosting primarily focuses on reducing bias, turning weak learners into a strong, highly accurate predictor. Question 20. What is XGBoost? XGBoost stands for Extreme Gradient Boosting. It is a highly optimized, state-of-the-art implementation of the gradient boosting framework designed for speed, flexibility, and performance. Like standard gradient boosting, it builds decision trees sequentially to minimize a loss function. However, XGBoost introduces several key innovations. First, it includes built-in L1 and L2 regularization directly in the objective function, which penalizes complex trees and prevents overfitting. Second, it utilizes advanced system optimizations, including parallel tree building, cache-aware data access, and out-of-core computing for handling massive datasets. Third, it has built-in algorithms for handling missing values and sparse data. These improvements make XGBoost incredibly fast and highly accurate, which is why it is the go-to algorithm for winning machine learning competitions and solving real-world business problems. Thank you for watching. If you found this video useful, please subscribe to SHR Trinity for more videos, and click the like and share buttons. Stay tuned for part 3, where we will cover data preparation and model evaluation. If you are interested in attending our live training sessions or have any inquiries, all our contact details are displayed right here on screen and are also available in the video description below. Feel free to reach out to us. We would love to have you as part of the SHR Trinity learning community.